Since target yeah, probably need it on this. No. Like that. One page. But I'm like. Okay, yeah, that's exactly the one. Okay. Okay. Yes. I probably will use that too, but this is just in case that. She said. If not, yeah. Yeah. Okay, question. And the first question about the advertising, I didn't get a whole number.
Oh, yeah, just because, so I rounded up on mine,
That's what I
just because you
figured
can't
as
have
well.
like a decimal, so.
I just wanted to make sure there wasn't something like crazy.
Oh, no, yeah,
Cool. Okay.
I get a decimal too, I just.
Cool, and
Yeah.
that's what I figured, because it works out, it would be round. When I was doing the Hessian to check for it, I got a negative at first, and then a positive, and then not a positive. And so, like, I didn't do it all the way, but you can tell it's gonna be 40 minus a absolutely huge number. This one is negative one.
Yeah.
Yeah. It should be, let's see.
Yeah, for sure. You have time to go to sleep or do you have stuff to do?
Oh, okay, so what I did for this one, so
You got things
because
to do?
you can solve this one by substitution, you actually don't even need to go to this sheet. So once you kind of plug it in, it becomes a 1D, a 1D. So that's how although in theory, it should work out both ways, but I think for this one, I think once you kind of plug it in, you just take the second order derivative of it's that 1D. That's what I did. And yeah,
Okay,
your math looks right.
that makes sense then. So just to plug it in, take derivative, set it equal to 0 once you have one in terms of.
Exactly.
Okay. Cylinder, I got the crazy values that you did.
Mhm.
The Hessian's pretty rough for those.
It is.
Oh, okay, I wanted to make sure that
Um,
because plugging in the like things to third powers and things to 2/3
oh, yeah,
powers.
yeah. This one also, I think, this one was also eliminated. You can plug in for this one, right? Although, oh, this was a constrained optimization.
It's only.
Yeah, so
you
I,
have a constraint.
so I think I did the same thing here. So because you plug in, you can treat it as like a 1D problem. So
Okay.
you don't have to go through the.
So as soon as you can explicitly write like. Then you treat it like direct
Exactly,
substitute.
exactly.
And you just won the method. Got it. Okay,
Exactly.
that's going to make my life a lot easier.
Oh, yeah,
because I was
yeah.
like, this is the worst algebra I've ever seen. Okay, so that probably also. Tussi's actually. It's not too bad.
Yeah.
Well, thank you.
Yeah.
That makes my life a lot easier than possibly several hours.
Oh, yeah, for sure. Okay. All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, good. Hanging in there. You know, things are probably getting busy for everyone. Things are gonna get busy for us too. So our midterm exam is next Thursday. So first thing I want to do today is kind of just talk about that a little bit in terms of what you can expect. We'll talk about format of the exam and what you can bring. And then after that, today's gonna be, we're gonna be kind of hopping around a little bit today. So first thing I want to do after we talk about the midterm is finish up our lecture notes on inequalities and strengths. So I have one last example to do with you guys. That has inequality constraints where we're going to use the Tucker conditions. Okay. So we'll probably do that for maybe the first half of class. And then from there, that kind of closes our chapter on the classical methods. And then we're going to start doing more modern stuff. And so, we're not really going to get into the modern algorithms until probably after the midterm. But now is kind of when we need to start kind of doing a lot of the prep work. That means we're doing a lot of MATLAB. Because all the second half of the course, we'll be working on MATLAB stuff, programming in MATLAB, programming algorithms, solving optimization problems in MATLAB. So we all need to have a good grasp of how to use MATLAB and just be really comfortable using it. So I have a pretty long review plan, so it'll probably take up half the lecture today. We'll spend all Thursday reviewing MATLAB and probably a good part of next Tuesday as well. Okay. My MATLAB review, it's kind of gone through a lot of transformations over the years. So it's designed to be interactive, and so once we get to that part of the class, I'll ask everyone to open up MATLAB and write a lot of scripts together, just so that you can kind of really kind of see what's going on in this. Because the thing with MATLAB, I like to think of your MATLAB skills as like a muscle, and so it's not something you kind of just watch someone do and then kind of pick it up yourself. It's something that you have to exercise and kind of do yourself in order to really pick up those skills. Okay. Because if and this is kind of true for all programming, where you can learn the syntax, you can kind of learn the language itself. That usually only takes a very short amount of time. It's actually in using the programs and using it in kind of novel and new situations. That's kind of when you start to really build your skills, build your confidence. So I'm hoping that we can through this review we can kind of build that confidence, so that once we get to the optimization algorithms, then kind of the learning curve at that point will be a lot less. Okay. All right, so that's the plan for today. Any questions on any of that before we get started? Okay. All right. So first thing, let's talk about the midterm exam. Okay, so midterm exam is planned for next Thursday. That's October 10th. Okay, so it's going to take place in class, and so please plan to be here in the classroom. So there's going to be no plans to offer it over Zoom. Okay. So on the exam, you'll see that there are two sections. And if you've ever had me for a professor before, the format is you're probably going to be familiar with that. But for those of you who haven't taken an exam with me, basically there's going to be one section which I call the short answer conceptual section. And so the idea with this section here is to test your conceptual understanding of all the concepts and ideas and theories that we've been going over in the class. Okay. So what you can expect during this section, that there's going to be four questions. Okay. So each of those questions is going to test you on something that's that's based on a concept, and you can and they're designed so that you can answer those questions in maybe 2 to 3 sentences that you're going to write out. Okay, so they're free response questions. In total, the conceptual questions will be about 40% of the total points on the exam. Okay. So I place a lot of emphasis on the conceptual information just because of I find that those are really important, especially for a class like optimization, where it's a lot of new concepts and a lot of new kind of ideas, and so that conceptual understanding is really important. The other section of the exam are going to be basically classical optimization problems. So these are very similar to the homework problems that you guys have been working on. Okay. So in these kinds of problems, I'm going to be giving you an optimization problem. I may give you the objective function, I may not give you the objective function, and your goal in all these problems is to find the optimal values of all the parameters. Okay. So basically that be kind of all the example problems that we. So I planned 3 problems for this section. And so this section primarily is going to be is well, not primarily, it's all going to be from homework 2 and homework 3. Because homework 1, you know, we didn't really do any problems on that homework that are really kind of appropriate for an exam. So you can expect, you know, maybe 1 to 2 problems from homework 2, 1 to 2 problems from homework 3. In total, there's going to be three problems. Okay. And this section of the exam is going to be worth 60% of the total points. Okay. So what can you bring? So so I allow you guys to bring 1 sheet of notes. So that's 8.5 by 11 inches. Okay. You can use both sides. You can handwrite your notes, you can type it, you know, whatever is most comfortable for you. Okay. So for the sheet of notes, you know, what I've kind of noticed a lot, and it's kind of trending upwards in the last few years, is that it's very tempting to just kind of take the lecture notes that I've posted, or take the homework solutions. Oh, by the way, I'm going to post the homework solutions later this week too, and just kind of, you know, print those on your cheat sheet and then just bring that to class. That's certainly a strategy that you can do. But generally what I recommend for people is to, you know, really take the time to write your own cheat sheet, because taking all the content that we've covered so far, and we've covered a lot, you know, we've covered a lot of ground so far in this class, and kind of interpreting it, kind of condensing it yourself, and then, you know, finding out what's the most important piece of information and put that on your cheat sheet. That exercise by itself is a great study tool. And so it kind of, you know, you kind of kill 2 birds with 1 stone, where, you know, you're reviewing the material, you're processing it, you're really committing it to memory. And, you know, second objective is you're making your cheat sheet that you're going to use on your exam itself. Okay. So I remember, you know, when I was a student, you know, whenever I prepared for exams and the professor let me bring a cheat sheet, you know, I probably spent about maybe 75% of my time just preparing my cheat sheet itself. And then the 25-30% of the time I spent actually doing practice problems. So that's kind of generally what I recommend for people. Besides that, you can also bring your writing utensil, of course. Pencil, pen, whatever, you know, is most comfortable for you. And you can bring a calculator as well. I don't really have any restrictions on the type of calculator that you can use. You know, so scientific calculator, graphing calculator, I think those are kind of the most common. You know, bring whatever's kind of most useful for you. Obviously, you know, you can't use your phone, or you can't bring a calculator that has any kind of mobile, you know, communicative technology or anything like that. So, you know, a regular, nice, dumb calculator you can bring to you. Okay. Another thing that I'm providing for you guys, I've already posted this actually, is a study guide for the midterm exam. And so if you're looking for it, it is on the page for week 6, which is this current. All right, so I definitely recommend checking out the study guide. The study guide is really going to help you prepare for the conceptual questions. And so once you kind of open the study guide, you'll see that I've kind of written it in a way to basically kind of give you a lot of conceptual questions for you to kind of answer yourself. Okay. Sometimes I take questions straight from the study guide, and so, you know, maybe one of the short answer questions will be something that's on the study guide directly. Most of the time I kind of ask questions that are kind of, you know, maybe not exactly what's on the study guide, but kind of indirectly kind of asking the same things. And so, you know, if you use the study guide and you can answer all of those questions and kind of really understand it, then you're in really good shape for it. Let's see, what else? What other announcements do I have? Stuff. I think that's pretty comprehensive. Any questions on the exam for next week? Okay. All right, and so, of course, up all the way up until the exam, I'll have office hours, and so I believe there are 5 more. Oh, question, yes.
We're gonna do review on Tuesday or just continue lecture?
We're just gonna keep going with the lectures. Yeah. So I think I have 5 more office hour sections until the exam. So I have office hours tomorrow, office hours Thursday, and then next week I have Monday, Wednesday, Thursday, before the exam. Definitely stop by if you have questions. Take advantage of those office hours as much as you can. Okay. All right, any final questions before we get started for today? Okay. All right, so let's pick up where we left off from last Thursday.
You're really.
My room is E220. So second floor, so on the same floor as E201, just down. You come out the elevator, you turn right, and then you turn right. Okay. So last Thursday, we were in the middle of covering constraint optimization with inequality constraints. Okay. All right, so I really just have one more example that I want to do with you guys. But I know we did an example last Thursday, but you always have to try to do some more. This one's a little bit more realistic, I should say. The other example we did last week was just a theoretical kind of math problem. But before we jump into that example, let's do a quick reminder of kind of the way that we actually solve this. All right, so when we solve problems with inequality constraints, okay, the main challenge that we have is that we need to determine which of the constraints are going to be binding. Okay. Because remember, an inequality constraint has the following form. I'm going to put it in standard form for you. And so inequality constraints come of the form, g of xi is less than or equal to 0. Okay. And the main challenge with this is that, technically speaking, if our inequality constraints aren't binding, we can have, in theory, an infinite amount of these inequality constraints. And, a lot of times they're not going to have any effect on our problem. And that idea is kind of encapsulated by the Kuhn-Tucker conditions, right? So the Kuhn-Tucker condition said that, ultimately there's kind of two fates for an inequality constraint. On the one hand, your inequality constraint could be binding and it has a big impact on your result. Okay? And so if our inequality constraint is binding, what that means that our equation, our constraint equation is satisfied in the equality form. And so in that case, we can actually treat it in our solution as an equality constraint. And we have, a lot of methods to do that for us. And so we can either do direct substitution or we can use the Lagrange multiplier approach. Okay. The other possibility for an inequality constraint is that it just has no effect on the solution at all. And so it's a non-binding constraint. And so if it's a non-binding constraint, we can thus ignore it in our solution process. And so if we can ignore it in the problem, we just kind of get rid of it. Okay. Mathematically, the way that we can do that is, we can set up basically a Lagrange multiplier problem, and we just set its Lagrange multiplier 2 to 0. Okay, but effectively, what we're doing is we're just kind of ignoring those things. And so the tricky part comes with determining we're given an optimization problem, determining which constraints, if any of them, are even binding to begin with. Sometimes it's obvious, sometimes you can kind of tell just based on intuition, just based on your analysis of the problem, which constraints are going to be binding, but sometimes it's not. And so last Thursday, we did an example where it wasn't really clear just by looking at the problem which constraints were binding. And so what we had to do in that case was we had to do a guess and check, right? So we guessed that certain constraints were binding, we solved the problem. If we found that the problem gave us a valid solution, then that's good. If not, then we guess a different combination of binding constraints. So the thing with these problems that, sometimes they can be very quick if you're able to kind of guess very quickly which combination of constraints is binding. Sometimes these problems can take a really long time because if you have a lot of inequality constraints and you're not sure which combination of 1, 2, or 3 of them are binding, you're probably going to be trying the problem a lot of different ways. Okay. So for that reason, the Kuhn-Tucker conditions, they're great in theory. And in fact, they kind of form the basis for a lot of the constraint optimization algorithms we're going to cover, much later in the class. But as a theory by itself, because we can only really use it in guess and check, there's a lot of limitations of what we do. Okay. All right, any questions on this? This was all just kind of a review last Thursday. Okay, all right, so let's do one more example of this. Okay, so in this example, let's kind of pretend that we're working for a manufacturing firm, and this firm is responsible for manufacturing refrigerators. Okay. So based on the orders of refrigerators that are going to occur over the next 3 months, basically, all the stores in the area have ordered in total 50 refrigerators for you to manufacture each month. Okay, so the factory has to manufacture at least 50 refrigerators each month. So each month, they're shipping out at least 50. Yeah, question?
When you're writing notes, you do follow your old notes, right?
Yes, yeah.
Where are you?
I don't know what page it is. It's on the the notes for constraint classical optimization. I think I'm on page 14 out of 16. So this is the third to last. Okay, so each month for the next 3 months, there has to be at least 50 on hand. So that means they have to manufacture at least 50. Okay. But your factory also has the ability to store refrigerators temporarily. And so what you can do, what this factory can do is that you can manufacture. So let's say the first month you manufacture 70 refrigerators, 50 of them you can ship out, but the rest of the 20 you can put into storage. So you can have, a really busy month and then just put whatever excess into storage just to save it for. Okay, so let's get some equations. Okay, so in this situation, the firm is interested in minimizing their production costs, right? Because it costs money each month to manufacture the refrigerators. Okay. So let's put some equations here. Okay. So the cost of producing X refrigerators, where X is the number of refrigerators you're producing that month, is given by the following equation. The equation is X squared plus 1,000. That's going to be our cost. It is going to cost some money to store the refrigerators as well, because you have to move them. You have to kind of make sure their electronics are properly stored away. So the cost that's associated with storing each refrigerator is $20 per fridge per month. Okay. So with that in mind, let's define our design variables. So we have a three-dimensional optimization in this case, and so we're going to have X1, X2, and X3. Each of these design variables here are going to describe the number of refrigerators that the company should manufacture in the first month, the second month, and the third month. And what we're interested in is we want to compute the optimal values for X1, X2, and X3. And of course, this is one of those problems where we want to minimize the cost. Okay. So that's the problem. And so, we need to write out our objective function based on what we know. And there's going to be some constraints as well. All of the constraints in this case are going to be inequality constraints. So we need to, determine which of these are what. All right, any questions on the setup of the problem? Okay. All right, so first thing we're going to do, let's write out our objective function. Okay. And so because the objective of this problem here is to minimize cost, our objective function in this case should represent the total production cost. And so we have those two equations that we have about, well, one equation and one relationship, right? So we have one cost that's associated with actually manufacturing the refrigerator each month. And we have the storage cost as well. Okay, so our total cost is going to be the sum of both of those things. Okay, so our objective functions, we have f of x1, x2, x3. So let's account for the manufacturing costs first, right? So if we kind of scroll back up here, you can see that the manufacturing cost is x squared plus 1,000. Where x represents the amount of refrigerator produced in that month. Okay. So we have three months to consider here. So we're going to repeat that equation 3 times. Each one for x1, one for x2, and another for x3. 1 squared plus 1,000. Plus x2 squared plus x3 squared plus 1. Okay. So based on that form for the manufacturing cost, you can kind of see why the company is interested in storing some refrigerators, right? Because each month, you have a portion of the cost that scales with the amount of refrigerators that you're producing, right? So that's the x squared component. That's pretty common, right? So the more parts or the more products that you manufacture, you need to pay for the labor, you need to pay for the time and all the materials that's required to make them, right? So that makes sense. But each month, there's also what's often called a flat cost that's associated with maybe starting up the machines, running the electricity in the building, and so on and so forth. Okay, so each month, you can see even if you produce 0 refrigerators, you still have to pay a flat cost of $1,000. Okay, and so it would be really nice if maybe the company produces maybe 150 refrigerators all at once. Maybe then you can save on some of the costs for later. Okay, but then we also have the storage cost as well. Okay, and so the storage cost is $20 per fridge per month. Okay, but that's any fridge that's in excess of the order for that month. Okay, so for the first month going in and going to the second month, right? Basically, any excess fridges over 50 is is going to be, you're going to add some cost in. If x1 is greater than 50, right, then we're going to tack on some cost of $20 per fridge. So mathematically, the way that we're gonna add that into our objective function is that we're going to say we're going to add some cost, and the added cost is going to be 20 multiplied by x1 minus 50. So you can see here that, if we produce, let's say 60 fridges in the first month, so X1 ends up being 60, then we are gonna add 200 times 10 to the total cost. Okay. And then we also need to add a cost for the second month as well, right? And so in the second month, if we produce over 50 fridges, and so total, if we produce over 100 fridges over the first 2 months, we need to add some cost for that as well. So to add that cost, we're gonna add 20 multiplied by the quantity, X1 plus X2 minus 100. Okay, so this portion right here, this is the storage cost for month 1. Right here is the storage cost for month 2. Okay. We're not going to add any storage costs for month 3 because this analysis is only going to cover up until the end of the 3rd month. Okay. In theory, if you were actually running this company, that's something that you would consider. But in this case, we're only worrying up to the end of the 3rd. Okay. So we're only going to add storage costs going from month 1 to month 2, and then month 2 to month 3. Okay. So that's our objective function. So it's quite busy. So you can see we have a lot of terms here. So we can actually, let's simplify this a little bit, just to make our lives a little bit easier. Okay, so what I'm going to do is I'm going to distribute, each of the 20s into the storage terms, then just going to add up like terms. Okay. Because right away we see that up top here we have 1,000 plus 1,000 plus 1,000. So of course all those can combine. And then we have some added constant terms at the bottom as well. Okay, and so if we add all those things, what we get is F 1, 2. First, we have all the squared terms, so X1 squared plus X2 squared plus E squared. So all those came from the manufacturing costs in the first 3 kind of parentheses. There's no other squared terms in our equation, so all of those are going to be there. Okay. Okay, next we have the linear terms in X1 and X2 that come from the storage cost. So the 40X1 and a 20X2. So both of those terms come from the storage cost. Okay. And then for all the constant terms, you can see here that we have 3,000 that comes from the first 3 parentheses. Okay. And then 2 minus signs here that come from the other. We have a minus 20 times 50. 20 times 50 is 1,000. So we're going to do 3,000 minus 1,000. And then we have a minus 20 times 100. 20 times 100 is 2,000. Okay. So 3,000 minus 1,000 minus 2,000. All of those, of course, are going to cancel out. And so our final objective function only has the x terms. Nice and clean. You don't have to simplify it, of course. You can just work with the original objective function. Sometimes that's helpful. Just because then it's a little bit easier to kind of see, which, when you take derivatives, which terms kind of go associated with that one. But a lot of times, it's better to simplify just to make your life easier when you're taking derivatives. Okay. Any questions on the objective function? Okay, good. Let's go ahead and write out our constraints. So all of our constraints in this problem are all associated with the same thing, that we have to fulfill the minimum order for each. 1. All right, so by the end of the first month, we have to produce 50. By the end of the second month, we have to produce 100 total fridges. And then by the end of the 3 months, we have to produce 150. Okay. And so in other words, what we have to say is that X1 must be greater than or equal to 50. We can of course put this in standard form. And so in standard form, we are going to subtract the X1 from both sides. So 50 minus X1, so that's going to equal to 0. Okay. And this problem, it doesn't really matter which side of the less than or equal to sign you can put. So you can very easily do X1 minus 50. That might be a little bit more intuitive. And so if we do X1 minus 50, then X1 minus 50 has to be greater than or equal to. Okay. So either form works. As long as you have 0 on one side, it's fine. Constraint. So that's constraint. That's the constraint that's associated with the first order or the first month. Called G1. G2. So at the end of the second month, we have to produce 100 total refrigerators. So one way we can split that is X1 plus X2 minus 100. Right. And then G3, our third constraint means states that at the end of the 3 months, so X1 plus X2 plus X3, we have to have at least 150 fridges at that. X1 plus X2 plus X3 minus 150. That's the third constraint that we're. All right. So all these constraints are inequality constraints, right? So we don't know which of these are going to be binding or. And so, we have to kind of go through our guess and check procedure. Right? So sometimes these results may be constraining, sometimes they're not. Okay. It all kind of, depends. So, looking at this, you may think that, we can try to make all 3 results binding, right? So, that basically requires that we produce 50 each month, but that may not be the that may not be the optimal result, right? And so in this case, if all 3 constraints are binding, the easy answer is just be X1 is equal to 50, X2 is equal to 50, X3 is equal to 50, right? That'll work. So that'll satisfy all the minimum orders, but that may not minimize the cost in this case. So there may be a better way to do this. Arrange X1, X2, X3. Maybe you front load a lot of the production so that you save some cost that way. And then, you produce less in labor. So we're going to go through that. Okay. All right, so let's try different combinations of the constraints. Okay. And so there's unless you have some good intuition here, it doesn't really matter which one that you start with. Okay. All right, so to try one right here, let's relax the first constraint, right? And so when the first thing that I kind of think about when I see this problem is maybe we can front load a lot of the production. So let's front load, maybe we can make X1 very big and then make X2 and X3 small, right? So the way that we can do that is we can, make constraint 2 and 3 binding, but then we relax and ignore constraint 1. Okay. So we're gonna treat this problem as if we're gonna ignore constraint. Okay, and so in this case, our other two constraints become binding, and so we change that inequality to an equality. We have x1 plus x2 minus 100 has to equal 0. Okay. X1 plus x2 plus x3 minus 150. Okay. Okay. So the traditional way to solve this is to, form the Lagrange function. So now that we have two binding constraints, and so we're going to have a Lagrange function with 5 design variables: x1, x2, x3, lambda 2, lambda 3. Okay. I'm just gonna use a little bit of a faster method here. I'm just gonna go with direct substitution. Okay. So let's use these constraints, solve them via direct substitution, and then plug them back into our objective function. The reason I'm going with direct substitution in this case is that, we have two equality constraints. Two equality constraints in a three-dimensional problem. That means we can eliminate two of the variables solve just a one-dimensional optimization, which is always kind of, ideal. Okay. So let's use our two constraints here to eliminate x2 and x3 from our objective function, right? And we'll try to solve for an optimal value for x1. Okay. So let's solve the first constraint there for x2. Okay. All right, so our first constraint in this part right here is x1 plus x2 minus 100. Okay. Let's solve this for x2. So I'm going to move 100 and the x1 to the other side of the equation. And what we get from that is x2 is equal to 100 minus x1. Okay. Then I'm going to take the second constraint because x3 doesn't show up in the first constraint. I'm going to solve the second constraint for x3. Okay, so our second constraint is x1 plus x2 plus x3 minus 150. We solve this for x3. So we have x3 is equal to 150 minus x1 minus x2. Let's plug our expression up there because we already have an expression for x2. Okay. So let's plug that into that equation there. X3 is equal to 150 minus x1 minus quantity 100 minus x1. Okay. Let's go ahead and solve the arithmetic in this case. X3 is equal to 150 minus x1, but we also have a plus x1 that comes from the second term. So the x1 terms are going to cancel out. Okay. We have 150 minus 100. So we actually get an explicit expression for x3 already, even without using the objective function. So we have x3 x3 is equal to 50. Right? All right, so that's good. Okay, so now let's go back up to our objective function and plug these expressions in. Okay, so now that we have an expression for x3, we have an expression for x2 in terms of x1. That's going to solve our objective function and just leave us with just one variable. Okay, so if we plug this back into our objective function, let me write out our objective function one more time. We have f of x1, x2, 2, x1 squared plus x2 squared plus x3 squared plus 40x1 plus 20x2. Okay, so let's plug in for everything is here except for x1. So we have x1 squared plus we have quantity x2 squared. We know x2 is 100 minus x2 squared. Okay. We know x3. We know x3 has to have a value of 50, so this would be a plus 50 squared. Okay.
Shouldn't it be 100 minus x1?
Yes, it is. Thank you. Yeah, thanks for catching that. Wouldn't make sense if we plug in for x2 and we get x2 right back. It's like that uncle that you're trying to get rid of from the party, but he just comes back in. Okay. Then we have 40x1, so that can stay the same because we're solving this equation for x1. And then we have a 20x2, right? So we're going to plug in for x2 again. So it's going to be 20 times 100 minus x1. Okay, so let's simplify this, and so let's FOIL out all the terms, and then let's combine like terms here. Okay, so you have x1 squared plus we have quantity 100 minus x1 squared. Okay, so if we FOIL that out, that's going to give us 100 squared minus 200 x1 plus x1 squared. Plus 50 squared, 50 squared is 2500. Plus 40x1 plus 20 times 100, so that is 2000. Minus 20x1. If there's some pause in this one, I'm actually solving this one from scratch right now. So in the notes, if you look in the notes, I actually solved this using Lagrange multipliers. I thought this would be faster, but it's still kind of taking up a lot of time. So regretting my choice a little bit here. Okay, so let's combine all the x1 squared terms. We have two of these terms here. So we have an x1 squared plus x1 squared. So that's going to give us 2x1 squared. Okay. Let's add all of the x1 terms. Okay. You can see we have three of them. We have a minus 200x1, a plus 40x1, and minus 20x1. Okay. So you combine all those together, you get a minus 180. And then we have all of our constant terms. We have 100 squared. 100 squared is 10,000. Okay. 100 squared, 2,500. We have 10,000 plus 2,500 plus 2,000. That is 14,500. And now our objective function is just one variable. Okay. So we're in a good spot right here, right? And so we took our three-dimensional problem and we've reduced it down to one variable, which is kind of the goal, right? So let's take our derivative. Yeah. 4x1 minus 180. So that's going to equal 0. Okay. So we have a simple expression here to solve for x1. Okay, so x1. We're going to move that 180 to the other side, divide by 4. Okay, so x1 is equal to 180 minus divided by 4. Okay. We do that arithmetic, and so we do long division here. 18 divided by 4, that's 4, remainder 2. Okay. We bring the 0 down, so we have 20 divided by 4, which is 5. Okay. So under this optimization here, right? We can use this to solve for x2. So x2 is going to be 100 minus x1, which is 3. We know already is 50. Okay. So that's our production schedule there. So we have x1. So first month we're going to produce 45 refrigerators. x2 we're going to produce 55 refrigerators, and x3 third month we're going to produce 50 refrigerators. Okay. Good. So remember, the way we got this result was that we relaxed constraint 1, right? Or we assumed that constraint 1 was unbound. So when you assume a result is or a constraint is non-binding, remember what you have to do once you do get your optimal values is you have to go back and check to see if your non-binding constraint was actually still satisfied. Okay, because to get this result, we completely ignored that constraint completely, right? And so this result here was not going to be beholden to that. And so it's very possible. In fact, you probably look at this and see that that's exactly the case. It's very possible that when you relax a constraint or when you ignore it, it ends up being violated in the end. And so to check if the constraint is satisfied, you're going to plug in the optimal values for the design variables and see if that's still good. Okay. Okay, so this constraint here only involves x1. So let's plug in our optimal value for x1, which is 45. We have 45 minus 50. 45 minus 50 is equal to 5. Okay. And this constraint is satisfied if minus 5 is greater than 0, which clearly it is not. Okay. What this is telling us is that for this problem, we picked the wrong combination of constraints. Okay. Yes, question.
If we pick a set of constraints and we find we violated the other one or one of the other ones, does that mean that has to be a binding constraint?
It's usually a pretty good indication. Yeah. So in this case, this tells us that constraint 1 probably should be. It's not a strict requirement, but there are kind of weird situations where if you find 2 constraints that will satisfy this one, even though it was not satisfied another time. But those are pretty rare. So usually when you have a case like this where you have one constraint that you relaxed, and it didn't work out, then you should make that one binding in the next. Your question over here too? Yeah, so in this case, in our next try, we should make the first constraint binding. Okay, so let's do try number 2. So actually, if you follow the notes, I actually try four different combinations. So I'm going to do one more just to kind of illustrate to you, and then I'll give you the right combination. Okay, so we know from this is that the first constraint probably should be binding, right? So let's make the first constraint binding again, but let's relax the constraint on the second. So our second constraint is x1 plus x2 minus 100 greater than or equal to 100. Okay. Let's assume this constraint now is non-binding. Remember, when we started this problem, intuition kind of told us that, maybe we can try to front load some of our production, to save on some costs, right? And so we've already tried, overloading x1, that didn't work out. Let's try, maybe amping up the production on month 2. That's kind of the result that we got in this result too, was that in try 1, we end up with x2 is equal to 55. So maybe it's going to be worth it to overload the production on month 2. Okay, so just like before, let's turn our other 2 constraints into binding constraints. Okay. Our first constraint in this case is x1 minus 50 must be greater than or equal to 0. Okay. If this constraint is going to be binding, we're going to turn this into an equality constraint. And so from this equation, we can see very quickly that x1 has to equal 50. That makes sense, right? So the requirement is that we have to fulfill our order, our minimum order of 50 fridges in the first month. And so in order to do that, we have to produce 50 fridges in the first month. Okay. And our other constraint is the third constraint. So that's x1 plus x2 plus x3 minus 150 has to be greater than or equal to 0. It's our third constraint for the problem, but it's the second one that we're considering for this try right here. Okay. Once again, we're going to turn this into an equality constraint. Okay, so we're going to change that inequality sign to an equality sign. And then what I'm going to do is I'm going to solve this equation for x3. We already know from the first constraint that x1 has to equal 50. So let's go ahead and plug that directly here. Okay. And then I'm going to move everything else over to the other side of the equation. Okay, so if we do that, so I'm going to do kind of a little bit 2 steps in 1 here. If x3 is equal to 50 is x2. And so if we simplify that, we get x3 is equal to 100 minus x2. Okay. So now that we have these expressions, let's plug it into our objective function. Because then we're able to get our objective function with 1 variable. Okay, so we have f. Now the variable that we're considering is x2. Okay. Okay, so let's go ahead and plug in. So first we have x1 squared. So x1 in this case we know is 50, right? So it's 50 squared plus x2 squared plus. And then we have quantity x3 squared. So x3 in this case is 100. 2 squared. Then we have the storage cost terms, and so the storage cost terms are 40 multiplied by x1. We know x1 is 50. Plus 20 x2. Okay. So that's just our objective function. I just plugged in for x1 and x3. Okay. And so that basically eliminates all our variables, and all we're left with is just a single variable, which is x2. All right, so let's simplify this. So 50 squared is 2500 plus x2 squared plus quantity 100 minus x2 squared. So that is 10,000 minus 200 x2 plus x2 squared. We're going to multiply 40 times 50. 40 times 50 is 2,000. Then we're going to add a 20 x2. Okay, so let's combine like terms. And so we have our 2x2 squared term. So we have 2x2 squared. For the linear terms in x2, we have a minus 200 x2 plus 20 x2. That is 182. And then we add all the constant terms. So the constant terms, we have 2,500 plus 10,000 plus 2,000. We have 14,500. Okay. So we have our objective function in terms of one design variable here. Let's take the derivative. We take the derivative of this, we get 4x2 minus 180, 0. Okay. All right, so if we solve this for x2, we get x2 is equal to 180 divided by 4. We solved this earlier. 180 divided by 4 is 45. All right. And so if we combine this with our previous results, and so based on our constraint equations earlier, we know that x1 is equal to 50. x3 we know is 100 minus 2, which is 55. Okay. So that's our result in this case if we assume constraint 2 is not right. Looks very similar to our try 1, right? Except we kind of just flip things around. Okay. Any questions on how we got this result here? Okay. So once again, we have our optimal result here. Let's check and make sure that the constraint that was non-binding, let's see if it still sets. Okay, so our constraint that we assumed was non-binding in this case was x1 plus x2 minus 100. So let's plug in our results for this. So x1 we know is 50. X2 we know is 45. And we're going to subtract 100 from that. And to do that kind of simple arithmetic, we end up with minus 5. So of course, and so we're going to check and see if that's greater than or equal to 0. Of course, it's not. And so once again, we end up with an incorrect combination in this case. All right. So once again, we've done all this work and we end up with something that's incorrect. Okay, so we have to try again. All right, so of course, the next logical thing to try is to say that maybe the third constraint is non-binding. I'm not gonna put you through that torture, and so I'm just gonna tell you the result. Okay. So try 3, we're gonna set x1 plus x2 plus x3 minus 150 greater than 0. So we're going to assume this one is non-binding, so this is the one we're going to ignore. Okay. So maybe you can kind of already tell what's going to happen here. And so if you look at our other two constraints, this is the only one that places a constraint on x3, right? So constraint 1, constraint 2, those put constraints on x1, x2. If we ignore this constraint, then there's nothing constraining the value for x3. So x3 can kind of be whatever it wants, if we ignore this constraint. Okay. But if you look at our objective function, our objective function, we're aiming to minimize the cost, right? And what's the best value for x3 that minimizes the cost? 0, right? And so we don't incur any cost if we produce 0 refrigerators in month 3. But of course, that can't happen, right? And so you can't produce 0 refrigerators in the third month. Okay? Because what you're going to get from the first two constraints, you're going to get x1 is equal to 50, and then you're going to get x2 is equal to 50, right? And so if you produce 50 refrigerators in the first 2 months, if x3 is 0, then you're not going to satisfy your minimum order. Okay. So this is going to lead to a non-valid result. Okay. So technically at this point, we haven't exhausted all of our options. And so, with 3 inequality constraints, the 3 combinations that we've tried is that, in each of the tries, we assume that 2 of the constraints are binding. Okay. And so you can keep going. And so you can, say maybe only constraint 1 is binding, constraints 2 and 3 are not binding, maybe only constraint 2 is binding. So there's a lot that you can try, right? But, from kind of doing all this, you kind of start to build some intuition, right? And so based on all of our trials here, it kind of seems like all 3 constraints are important. Okay. So in try 4, let's assume that all 3 constraints are binding. Okay. And so all three constraints are binding. This is kind of a unique kind of situation where, we have three constraints, right? If we assume all three are binding, then we have three equality constraints for three design variables. And so in other words, we have three equations that we have to satisfy for our three variables, okay? And so in this case, we have a situation of what's called a trivial solution, right? And so in this situation, if you have the same amount of equality constraints as design variables, the objective function doesn't even factor into it because all three design variables are going to have their values specified by the constraints. And so, the objective function is kind of mute at this point because we don't have any degrees of freedom. So this is pretty rare, right? And so this is not always going to happen. In fact, usually if you're posing it as an optimization problem, usually you have some degree of freedom to change the values. It's just that this is one of those cases where it's not like that. Okay. Now this may seem kind of a disappointing result because we spent basically this whole lecture doing this example only just to come up with a solution that you have to produce 50 each month. But I at least wanted to show you one of these types of problems to show that it can happen. And this is kind of what it is. Okay. All right. So very quickly, if all three constraints are binding, we have x1 minus 50, 0, x1 plus x2 minus 100 has to be 0, x1 plus x2 plus x3 minus 150 has to be 0. Okay. Three equations for our three unknowns. We don't have an optimization problem anymore. We have an algebraic problem. And so we can kind of solve it using algebra. From the first equation here, we can see that x1 is equal to 50. Thankfully, this is a pretty easy kind of algebraic system to solve. We just kind of go from one equation to the next. Okay. We plug in x1 is equal to 50 into the second equation. And so that's going to give us x2 is equal to 50. And we plug that result into the last equation, and then we end up with x3 is equal to 50. Okay, so this is one of those situations where you're going to go through all this work, and you're going to do all this work just for your manager just to yell at you because you're like you wasted all my time just to tell me something I already knew. But now with certainty that this is the right thing to do, right? So you ran through the analysis and you came up with the obvious answer. Sometimes the obvious answer is the right answer. All right, any final questions on this? Okay, all right, so this is the cutoff point right here, right? And so this is the cutoff point for the midterm. So anything that we cover after today is not going to be on the midterm. Okay, so this is kind of the last topic that I'm expecting for the next week. Okay. All right, so thank you guys for coming today. I know this example kind of took longer than I thought, but hopefully the whole process will make sense. When we come back on Thursday, we're going to start our MATLAB review. So definitely bring your laptop with MATLAB. If you're joining on Zoom, make sure you open up MATLAB because it's going to be a fairly interactive session. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Thank you.
Thank you. the surface and everything.
Yeah.
So I was setting it up. Exactly. So it's just.
Exactly, yeah,
Okay.
we have one constraint, which is just the volume, and then your objective function is gonna be the surface area.
Okay.
Thank you.
Yeah.
Then the guy may have done it the other way, and I was like kind of getting confused with it.
I think the example you did in class was the other way, and so the
Okay.
homework I gave you the opposite side as well.
Hello.
Hey, Josh.
So just double checking, for most of these multivariable, if we have constraints, we can generally avoid the Hessian if we have.
Exactly, yeah, if you
Like,
can
if
avoid
we have like n-1 constraint.
Exactly.
N being,
number of design.
yes.
Yeah,
Okay,
yeah, you want to
That's-
avoid doing that as much.
I see why, I
Yeah.
think I've been so pre-programmed, because I did like, analytical methods in engineering, and we did some crazy
Oh,
stuff with
I
it,
bet,
and
yeah.
also, like, controls. And so there were some like absolutely beastly
Oh, yeah, yeah.
determinants, so I'm
Yeah.
like, okay, this is my life. Of course I'm back here, but I was looking at it and I'm like, man, no, I don't remember it being this bad.
It's not bad to have that mindset, it's just, yeah, I'm not,
Okay,
I try to be nice when.
that makes sense, because I was like. What if oh. Okay, cool,
Yeah.
that checks out. that-
Especially within the context of optimization, there's, like I said.
There's a lot of logic involved
Exactly.
in it, and that's one of the other things with that, because like with 3C where we're in the 2x2 meter room, that one, I look at it and it's so obvious that has to be the solution. I don't know how much math you want to show that, because it's very clear, like you need to get as close in the X direction.
Yeah,
You need to get it. Is it okay to even write stuff like logically, you need to get as close as possible to the X,
Yeah,
so
you
this
can
is
do that.
fine, and that's fine.
well,
There's-
I still want you to go through the math in this case.
Okay.
It's actually pretty short, because the constraints are pretty simple in this case.
Okay.
It's, and and you use the distance formula.
Got it.
So it's even if you do the math, it's pretty short.
Okay,
Um,
cool.
the only thing
But
I
we
would
could even
recommend-
start with like that, like
Yeah.
saying logically, we know it has to, you have to get as close as possible in the
Exactly.
X direction. You have to get as close, this is the verification.
Exactly,
basically.
exactly. I
Because
like giving
then
these
it's-
problems because it's, you know what the solution should be, and then, you go
Okay.
through the math and you're like, all right, that confirms.
Cool, I
that."
wanted to make sure, especially because I hadn't fully processed avoid the Hessian at all costs.
Yeah, yeah.
To that, I was like, oh man, if I'm gonna go through, I wanna make sure that I can't just say like, obviously, we gotta.
It is very obvious in that case, but yeah, I want you to go through the math just to.
Okay, awesome. That's a lot better than the math I was about to do.
Oh, yeah.
So I'm very happy there. Cool. Is there any time that I would be able to drop into like office hours other than, because I have the class after yours? on
Yeah,
Monday, but I know the Thursday, but is there any other time if I had other questions?
this week I'm pretty busy,
Okay.
so Thursday, 1 o'clock would probably be the best time.
Okay, I can do that. for
Yeah,
sure.
let's do that. Next week I think it'll be a bit more free, so next
Awesome.
week, let's talk next week.
Cool, just in case, with the two classes especially, I'm like, oh man, I really wish I didn't have like the class right after yours, because I have the two exams with you, and I was like,
Yeah.
oh my god, that is tight.
Yeah.
Cool though, that makes a lot of sense, and that made my life a lot less painful.
That's good, that's good.